All right. Thank you guys for coming. And let's get into it. So just a little bit about me to start. So my name is Olivier. If you want to reach me, LinkedIn is the best way. You've got my barbaric URL on the screen now. And I work for a company called Acoustics. And this year is actually the 40th birthday of Acoustics. So we've been doing this for a while. So what is it that we're doing? We make big speakers. So we tend to say, you might have not heard of us, but you have definitely heard us. So if you've gone to any large-scale event, there was like a little sporting event that I'm not allowed to name that took place in Paris over the summer. Our stuff was used there. So we make very big speakers. We also make very small speakers. The biggest speaker we make is 160 kilos with 20 speaker drivers in it. We also make electronics products, so mostly amplifiers. Also network switches, because when you're a speaker company, now you need to make your own switches to move audio over the network. And we also do quite a lot of software. So a key part of what we do is acoustic simulation so that our customers can deploy our products in the best way possible. So that's our sound vision acoustic modeling software. We also do remote control and monitoring of our amplifiers. You imagine if you have 200 amplifiers and you want to turn the volume up, you're not going to walk to 200 knobs and turn them one by one. So that's controlled remotely via this software. And just over 10 years ago, actually, we started diving into immersive audio for live events. And so that's the product I work on. It's called Elisa, and this is a screenshot of the control interface for it. And you're welcome to go to our website and learn more about it. There is a desktop version that runs on Mac and Windows, and it's completely free. So if you want to play with spatial audio, go download it. So as I said, our stuff is used in a range of different applications. So theaters, sporting venues, music venues, big festival stages, everywhere. Very important thing first, I'm hiring a C++ software engineer in London. I'm looking for someone with a strong product mindset and the development. You'll be working on all aspects of product development. So UX, UI, DSP, networking, interoperability with third-party system, optimization, profiling, and cross-platform work. So macOS, Windows, Linux preempt RT. List of requirements on this job ad might be a bit daunting. Don't hesitate to apply if you don't feel you match all these requirements. And don't hesitate to come talk to me to talk about the job as well. So why this talk? So this talk is called Docker for the audio developer. And that's actually a little bit of a lie. You'll see that there is very little about audio in this talk. But I called it like this because I find that audio developers, because of the nature of the products we're working on, we tend to have quite diverse area of expertise and interest. So UX, UI, workflows, signal processing, multi-threading, optimization, lock-free programming, networking, all these things. And what I love with this crowd is I know like you guys are very curious people. And so I want to use this as an opportunity to invite you to explore and get a deeper understanding of the systems you see every day. And Docker might be one of us. Docker's actually everywhere in all the cloud products you use. But maybe you're not using it yourself. So who has heard of Docker before coming to this talk? So almost everyone. Who has ever used it on its own at least once? Okay, quite a few people. Who are using it daily in their workflows? Okay, so not so many. Okay, so that's good. I think there'll be takeaways for everyone. And so this talk is also to show my love for Linux. I think Linux and open source is amazing, and the reasons will become apparent during the talk. So what this talk is about. So we'll learn some things about Docker, what it is, how it works, what it's for. I'm not a Docker expert. I'm an audio developer. I use it in my workflow. It's part of my CI pipeline, so I can say I'm using it daily, but I don't really interact with it daily. My CI machine does. And this is definitely not a tutorial or a collection of best practices or anything. This is really, as I said, an invitation to explore. So, and there will be some resources to look at the end. So we're going to start by exploring, and then we'll see 2 concrete use cases. So using Docker as part of a CI pipeline, and to get a little bit of audio in as a way of running a third-party audio application on the Linux audio computing platform, which is the ELISA processor that I talked about at length last year. All right, so let's explore. So best way to start diving into a topic, either ChatGPT. Some people use Claude. I'm still old school Google, so I just Google Docker. And we have this nice little summary from Wikipedia. Docker is a set of platform-as-a-service products that use OS-level virtualization to deliver software in packages called containers, blah, blah, blah. Okay. So OS-level virtualization, packages, containers. And some things that you guys might be wondering is about this. So is Docker just a VM, or is Docker just a root? And we'll be answering this today. So we talked about OS-level virtualization. So first question is, what OS? So Docker is mostly Linux software. There is an application called Docker Desktop that lets you run Docker on Windows and Mac OS. And to do this, they use a Linux virtual machine on your Mac or Windows machine. So on Mac OS, they use, I don't know what kind of virtual machine. On Windows, they use Windows Subsystem for Linux. So we're not really going to be talking about that. And there's also Docker for Windows that supports Windows containers, so that's a purely Windows ecosystem. Never used it, also not talking about that today. So this talk is solely focusing on Linux. So let's begin. So I'm on a pretty old Debian system. So that's Debian 10, kernel 4.19. So that's pretty ancient by today's standard. So it's 2 releases behind. And if you look at the docs, you'll see like one of the commands that will come up very often is Docker run. And Docker run allows us to run a container. And it will ask you for an image name. So we might Google for some image names, and we'll find there's an image called Debian Bookworm, which is Debian 12. So 2 releases ahead of the host system I'm running. And so if we do this, we'll see, okay, unable to find image Debian Bookworm locally. So it's pulling it. We don't really know from where, but there's some kind of download happening. So yeah, okay, yeah, downloaded, cool, okay. And then nothing happens. So that's all you see. But we learned already a few things. So there's this concept of image, and there's some kind of remote server. And this remote server is called the Docker Hub, and is a way of sharing images. And we'll talk a little bit more about that later. But otherwise, command exists there. Apparently, we've downloaded something, but nothing has happened. So, what's an image? So, if we run Docker container ls, we can list the containers that are running. And with the -a flag, we can also see the ones that are not running anymore. And what we can see here is there was a Docker container that ran using the image we specified. Apparently, it executed a command called bash, and it exited 16 seconds ago. So something did happen, we just didn't see anything happen. And the reason why is because bash is an interactive program. So if you don't give it a shell to interact with it, it will just exit immediately. So we can do the same thing, but run Docker in interactive mode with this -it flag. So E is interactive mode, and T is to allocate a sudo terminal. And if we do this, we get a shell. Cool. So somehow I became root. So that's interesting. And the host name is also different. So I look to be on some kind of different machine. So the question is, where are we? And so let's try to figure out where we landed. So I guess first thing we can try to do is ls. Let's see what's there. So we're at the root of some kind of file system that looks like a typical Debian distribution. So we've got a bin, a boot, a dev directory for our devices, file system, a home directory, a root directory. Looks like a normal system. So let's see what version of things we're running. So let's call bash version, and we see 5.2 something. And now let's look again on our host system, which, as you remember, host system is Debian 10, and the container is Debian 12. And we'll see we're running bash 5.0. And sure enough, if we look at the Debian packages list, we see on the left here that on Bookworm, so Debian 12, this ships with bash 5.12. And on my host system, it ships with Debian 5.0, so that all matches up. So it looks like we're running some different distribution. Okay. So we're definitely not on our host system. So let's see what we have in there. Let's see in home. Okay, nothing is home. On my host system, I have some of my coworkers who have been working on this machine. So we look to be on a completely different machine. We're seeing a different file system, and we're having different versions of the binaries. Let's look at other things. So can look at our IP address. On Debian, you can use the IP command to do this. And so we have an IP address. Okay, cool. That's good. So that means we have some networking capabilities. And again, let's look on the host system. And on the host system, I have a network adapter, a different IP address. And there's also this weird Docker 0 network that appeared that wasn't there before I installed Docker. And you can see that the IP addresses look to be in a similar range. So in the container, I'm on this 172.17 subnet, and it's the same for this Docker 0 virtual adapter that was added on my host system. So far, this could be a virtual machine. That's a typical thing that hypervisors will do, because you'll likely want networking in your VM. And a way of doing this is to create a virtual device inside of the virtual machine, and you'll need some kind of virtual network adapter on the host system, and then they talk to each other. So we're still not so sure. So we're on a different system. So far, could be traditional virtualization. So let's look at the processes that are running in this container. So we can do this with this ps command. And if we do this, there's not much running, actually. So there's bash, the shell we'll end it in, and the command I'm running right now. Okay. That's not much at all. That's kind of weird. Like on a Linux machine, like a full-fledged Linux machine, you would expect a lot more processes to run. And so to hammer that point home, if we do this on our host system, which is a regular Linux install running on a physical machine, we would see these kind of things. So these are the square bracket things. These are kernel tasks. So these are not really started by a process; they're started by the kernel themselves, by the kernel itself. And these are used to perform housekeeping by the kernel. So, for example, when you need to move a thread from one CPU core to another CPU core, there will be a kernel thread that will do this. And these are these threads that are between square brackets. So this migration task, for example, is achieving that. So you'll have some of those, and then you'll have some system processes. So for example, Debian uses systemd as the main service management system. And you'll see this very important process, the process with PID 1, which is the first one that started, the init process. On Debian at some point will spawn systemd, which will then spawn systemd logind, which then allows other users to log in and so on. So that's what we would expect on a traditional system, and we're not getting that in our container. We just have this bash process, which somehow was PID 1. So how's that possible? How could just bash run in a Linux environment without all the rest of the stuff? So at this point, we can try to also wonder what Linux version we're running inside that container. So we can, same command as we ran earlier. And we see like the same thing as on the host system. So that's kind of weird, because Debian 12 is supposed to ship with kernel 6.1. And I'm running Debian 12. I had the bash version that I'm supposed to get in Debian 12. But somehow I'm running the the Debian 10 kernel. That's kind of strange. How is that working? So at this point, like, you should have a serious doubts about being in a VM. So only a couple processes running, only one process running actually, this bash process. We're seeing the same kernel as the host. We're not seeing any kernel management tasks that should be there, although we do see a different file system and different program versions. So let's try to figure out what's happening. So let's do a little bit of detective work. So we're going to try to connect the dots between the host and the container. And for this, we're going to try to spawn some clues within the container, and we're going to try to find these clues back from the host system. So you can imagine, I don't know if some of you are into caving. I know that's kind of a weird occupation, but that's what people who enjoy caving like to do, is they find one cave, they find another cave, and they're wondering whether these two are connected or not. And they spend a lot of time and effort to try to figure out. And it's not easy because sometimes you can't go in there. And here it's a little bit the same thing. We also don't really know where to start. There are so many different options, different paths we could take on both sides, and hopefully we meet in the middle somewhere. So to do this, I'm just going to create a new folder. I'm going to call it Vim workdir. I'm going to cd into that, and then I'm going to run Vim as a background process. So that's pointed as process PID 603. And sure enough, if I look at the processes that are running on my machine, and I have my bash and my Vim that's running in the background. Cool. And we can also use the proc file system to check that the working directory of this process is what we expect. So if we look at what the cwd sudo file points to in the proc file system for this PID, we see, okay, it's pointing to Vim workdir. That's what we expect. So by the way, for those who haven't played with the proc file system on Linux, it's awesome. That's where you can get a lot of information about all the running processes. Okay, so we do this, cool. And also, let's leave another clue. So we're just going to write a file, send hello from the container, and write this in a file called hello.txt on the root of the file system within the container. So let's try to connect the dots. So now I'm back on the host system, and I'm going to look at all the processes that are running, and I'm going to grep for Vim, see if we can find that process that's running in the container. And sure enough, we find a Vim process, but somehow it has a different PID. So at this point, you might be wondering, oh, maybe there's another user logged into the machine that's also running Vim, and you check, and nope, there's no other user logged in as root running Vim on this machine. So that's kind of weird. So let's see what is the working directory of this Vim process. Sure enough, it's Vim workdir. It's the thing we just created in the container. But Vim workdir doesn't exist on the host system, which makes sense. We've created it in the container. So how come we can see this from the host? We see a process that's running. It has a working directory that somehow doesn't exist. Okay, weird. Okay. So maybe now you're thinking about something called a CRUT. So for people who have never used CRUTs on Linux, CRUTs are a way of making a process believe that the root of the file system is in a different place than it is. And a typical use case for a CRUT is, let's say you're implementing a web server. Web server will need to read files to serve them to the clients. And it might also need to store temporary files somewhere, maybe caches, or maybe some users upload files using an HTTP post command, so you need to store them somewhere. And so you're using already access rights, like, so that your web server doesn't run as root, it runs as a different user, and this user is not allowed to write everywhere. But another layer of security, and I'm using security with quotes, it's more to protect you against bugs in your software, preventing your software from writing in places where it shouldn't be. You can CRUT your web server in a different place, and then that web server can only see those files and write to those files. So they're not super secure. There are many ways of escaping CRUTs. Don't use them for security, but they can protect you from stupid programming bugs, and they're often used in Linux. So a way of checking this is to looking at the root sudo file in the proc file system for the PID. So now I'm using the PID that I'm seeing from this system. Somehow it changed PID, so let's just roll with it. And no, okay, it's just pointing to the root of the file system. So it's a non-crooted system, non-crooted process. Sorry. So okay, so that's not the answer. So I think we have already two answers to. We have answered our two questions that were frequently asked on Google. It's definitely not a VM. We're seeing the same kernel as the host system. We're seeing these processes between the host and the container. And it's also not a root. So, okay. So let's recap. So file systems appear different. The network interfaces appear different. Kernel is the same. Processes in the containers can be seen from the host, but with different PIDs, and the processes from the host can't be seen from the container. So let's try to do a little bit more research. So something we haven't looked at is the mounts. So we're back in the container, and we can look at our mounts. And here we'll see something pretty strange. So the root file system in the container is some overlay FS, which is kind of weird. So overlay FS, for those who are not familiar with, is a kind of union file system. And it's a way of taking two file systems and you superpose them on top of each other. And so you have what's called the lower dir and the upper dir. And then you mount this in a place where you see the two superimposed on top of each other. And any changes you make onto that mounted file system are reflected in the upper dir, not the lower dir. And a use case for this, for example, is a live CD. For people who have used Linux live CDs, a CD-ROM is obviously like a read-only media. But Linux needs to write into a bunch of different locations just to be able to boot and function. So when you mount a live CD, your lower dir will be your CD image, your Linux image, and then on top of that, you will mount an upper dir, which will typically have backing on a RAM disk, on a temporary file system. And then your Linux system functions as normal, and you don't need to do any other work to have a Linux system working on a read-only file system. And then once you turn off this machine, obviously your upper dir is stored on a RAM disk, so it just disappears. So that's the typical use for overlay FS. And but so you would expect the lower dir and the upper dir to exist in the file system you're in. And here, if we look at those, this var lib docker overlay whatever, this doesn't exist within the container. So this is weird. Like somehow we managed to mount an overlay FS in the container using directories that don't exist. That's really weird. So let's look from the host perspective. And this is what you would typically expect on the Linux system. You would expect some kind of block device. So in our case, dev SDA2, which is an SSD in my machine, with some kind of regular file system. So in this case, ext4 mounted in your root folder. And then maybe some additional file systems. And that's also what you would see on a VM. For a virtual machine, you would have a virtual hard disk, and inside your VM, you would see that virtual block device, which doesn't exist, but to the kernel, it looks like any other block device. And also, we see this overlay, and things match between this overlay and what we've seen in the container. So the upper dir and lower dirs are the same, but the mount point is different. It's this mount point in var lib docker, some kind of weird hash. So that looks promising. It looks like maybe we've seen where all these files live. So let's try to see. So we're still on the host file system, and we're going to cd into one of these lower dirs of this overlay file system. And look at what's in there. And that looks like a Linux install. So let's try to run the bash that's in there. And if the bash that's in there is the bash version we expect for Debian 12, then that's telling us, okay, we found it. That's where the container files live on the host system. And if we try to do this, oh, it doesn't work. And that actually makes sense because this Debian 12, this bash has been compiled for Debian 12, which has been compiled with a newer version of GCC and a newer version of the runtime GCC library, which we don't have on our host system. So we can't run this bash on the host system. And that's because dynamic linking is the default on Linux distributions. And why do we do dynamic linking? This is we can get a smaller distribution footprint. So if you have many programs that depend on the same libraries, you only need to have one copy of this library on your system. That also makes it considerably easier to deploy security and bug fixes, because if you depend on a library that's compromised or has a bug, the distribution maintainers can just push a fix to this library. And as a user of this library, as a developer who's using this library, you don't have anything to do for this to be fixed. But that's a lot of maintenance from the distribution maintainers. And what this means is you can't move one executable from one distribution to another. So between Debian and Fedora, between different distribution flavors, or even between different versions of the same distribution, because one of these crucial libraries that's shipped in with your distribution that almost everything depends upon is the C runtime library. And you have only one of those. So that means you're stuck with the versions that are provided by your package manager. And we'll talk a little bit about that later. But this is exactly the problem that containers are here to solve, to let you run different versions of the software, regardless of what the host system is. So let's try one more thing. So we talked about CRUDs before. So I'm still in this directory on the host file system where we found all the files that are in the container. And if we CRUD here, now to all the processes that are going to be running here, they're going to be seeing the same file system as what the container is seeing, essentially. And now if we run bash, that works because it's going to be using the libc of the container image. And we get our bash 5 to 15, which is the Debian 12 version. Cool, so that works. So looks like we figured out at least where the image is, but when we looked there, we didn't find the file we left as a hint. We only saw like the files that were already there when the container was started. So if we look again in these mounts, we will see that there is this, there was another directory, which is the upper there in this overlay FS. And it's named, it ends in diff, which kind of implies, okay, it's what the user, when the container is running, has added on top of the original image. So we can go in there and list, and sure enough, we find our Vim working directory that we created. And we find our hello.txt file. And if we cat it, we see hello from the container. And now we can try to send a message back to the container. So let's echo hello from the host at the end of this file. And then go back into the container, cat hello.txt, and we see both. So what we're showing here is that the file systems are actually the same. We can communicate between the host and the container, and there is no overhead to that. So how does this work? Because we figured out, okay, it's not a CRUD. We still haven't answered why we're seeing different PIDs between the container and the host. We're also seeing different mount points. So there were some common things about the arguments of that overlay file system, but we're still mounted in a different place. So we want to answer that. And sorry, there's a typo there that should say PS3, not P3. So we can run the PS3 command to see a little bit what's running on the host system, but as a hierarchy. And we'll see, okay, there's Docker D, so that stands for Docker daemon. That makes sense. We've installed Docker. We imagine some stuff must be running. But crucially, we'll find this container D thing. And that's where our Vim is. So our Vim is a child process of this container D thing. We never install container D, so what's that? So let's do a little bit of Googling. So we Google, we find a project page. Containerd is an industry standard container runtime with an emphasis on simplicity, robustness, portability. And if we see what's using containerd, Docker is using containerd. Okay, so that makes sense. That checks out. It's a dependency that Docker uses, and it was abstracted away from us. And if we look a little bit at the Docker project history, we'll see that this was actually started by Docker, and they pulled it out of their main code repository and donated it as an open source project. So Docker and containerd are heavily related. And so if we just Google, how does containerd work? Containerd is a runtime built to run containers, okay, yeah. It's an abstraction layer, interesting, which manages namespaces, C groups, and union file systems. So union file systems, we talked about it, that's our overlay FS. But namespaces, never, I mean, I've heard about C++ namespaces, but that's all. And C groups, we'll come to that a little bit later. So namespaces, okay. So Google Linux namespaces. You find the man page for Linux. And there's a description. It's nice, friendly to read, short. So a namespace wraps a global system resource in an abstraction. Second time we see this word. So that the processes running within the namespace have their own isolated instance of the global resource. One use of namespaces is to implement containers. And then there's a list of namespaces that exists, and I have taken a subset of it. So there's a network namespace, which isolates network devices, stacks, and ports, a mount namespaces, which isolate mount points, and a PID namespaces, which isolates PID. And there's also a pseudo file system, as everything on Linux, to inspect what namespace a process is running in. So if we look on our host system, we can use the NS folder inside the proc file system and look for the PID namespace and the MNT namespace. And so here, this process, the 2728, it's the bash session that I'm running in my root process. So, okay, so I'm seeing some numbers. Okay, cool. If I look at the host system dlogin D, you can see that the PID namespace is the same as my bash session, which makes sense. They're both processes running in the host. Normally, they're in the same namespace. But then, the Vim that's running in the container, you can see that it's running in a different PID namespace and a different MNT system. And so that's the trick that Linux uses to pretend to implement containers. So that's a key feature of the Linux kernel that makes containers possible. So this is something I want to stress that's very important. Containers wouldn't be possible without deep support within the Linux kernel, which allows you to pretend to have processes think that they're running in a different environment, see different PIDs, different network interfaces, and different mount points. So let's recap. So why do we need containers? Containers is our ways of packaging an application with all of its dependencies. So let's say you're a Debian 12 developer, you develop on Debian 12, you want to ship your application to someone who's running some different distribution. If you package it in a container that has all the Debian 12 dependencies, they can run them on their host system, whatever the distribution they're running. So this is a little bit a way of avoiding the Linux version of DLL hell, which we kind of saw, where I tried to run a bash that was compiled for Debian 12 on Debian 10, and that just doesn't work. And that leverages several Linux kernel features. So namespace is the main one. Overlay FS, also a super cool feature of the Linux kernel that allows you to superimpose file systems. And C groups, so C groups, we haven't really talked about it. It's a way of managing resources used by processes. So you can use C groups to limit the amount of CPU time a process can get or the amount of RAM a process can get. And that way you can also further control the usage of resources within your containers. So why is it better than a VM? No hardware virtualization needed. So to implement containers, you don't need to write a fake hard drive driver, a fake network interface driver, a fake GPU driver. You don't need to do any of that. You don't need to reserve any system resources. So if you're running a VM, you'll have your virtual CPU and it needs to run virtual RAM. And when you start it, you give it that RAM. So that means on the system with 16 gigs of RAM, the number of VMs you can run is very heavily limited because you're going to be running a whole operating system in each of those VM instances. And like modern OSs needs at least a couple gigs, right? So you're very quickly limited in the number of VMs you can run on a given machine. There's also no kernel and OS to boot when launching a container because we're just essentially launching new processes in new namespaces, so that's super quick. Launching a VM requires an entire operating system to start up, so that takes time. So it's fast and light. And the part we're going to talk a little bit about later is the tooling that Docker provides that makes managing containers, images, running them, and creating them awesome. So there's just one double-edged sword with this method. So the fact that we are not virtualizing means we're running the same kernel as the host. And so if some of your programs in your containers rely on some specific kernel features to function, they won't work. So that's maybe the only, like the main limitation of containers. So for example, there are VPN services that require some kernel features to work properly, or that install kernel modules to work. If you try to use this within your container and your host kernel doesn't have that installed, it won't work. So now is maybe a good time for a little intermission because I would like to introduce you to one of my favorite quotes in software engineering. So we saw that word multiple times, Docker containers, they're an abstraction. And there's a quote by this guy, Joel Spolsky, created a little website that's called Stack Overflow. You might have heard of it. And he wrote this, the date is wrong, sorry, it's in 2002, so 12 years ago. All non-trivial abstractions, to some degree, are leaky. And he calls this the law of leaky abstractions. And what he means by that is you can try to, we create abstractions as developer to hide some of the details, and we're really doing our best to trying to hide them, but somehow we never succeed in making this work. And so with Docker here, you saw that although within the container, it looked like I was in an isolated environment, I was seeing some details from the host leaking through that mount point because I could see where the lower dir and the upper dir of my overlay FS were on the host file system. So that's a leak. Another leak is the kernel. I could see the kernel version of the host file system. And the problem with that is as software becomes increasingly complex and we build more and more abstractions, at some point, you always end up finding something a little bit weird. Something doesn't work quite right. Like maybe you're writing C++ and it's really fast, and one day like you just swap 2 lines, and now it's really slow. And somehow you have to go to Compiler Explorer to look at the assembly code to understand what's happening. And you're like, wasn't the whole point of a compiler to abstract how the CPU works in the assembly? And sadly, according to Joel, and I tend to agree with him, it's impossible to achieve. Which makes being a programmer very interesting because we can have these talks like today. All right, so we got just a little bit of time left to look at 2 examples. So first one, Docker for a CI system. So our goal is to create an environment to build a Linux executable for a target distribution without having to manually install all the dependencies, and also without having to care about the distribution of the system that's actually going to be performing this build. And we want to use this environment as part of a CI system. So for this, we'll need to do a custom Docker image. And the way you do this is with something called a Docker file, which is the recipe to build a Docker image. So it's a very crude example, and I invite you to look at the documentation. These are I've really compressed this as much as possible to make it fit on size so that you guys can get the concepts. So usually you'll start from a base image. You don't build a Linux system from scratch. So for example, we could start from Debian Buster, Debian 10. And then maybe we need some dependencies to be able to build our software and run it. So we can install them by using the run command. Maybe we need CMake, and another way of avoiding the DLL hell on Linux is to build from source. So like the CMake version that Debian gives me is not the one I want. So here I decide to just build it from source. So I set my version, I download it using wget, I unpack the archive, I configure it, make it, install, and then I've got the CMake version I want in my image. Then maybe we'll want this to run as a specific user. We probably, as you saw in the container, I was root, that's the default. You probably don't want your things to run as root, so we'll create a user, where that user, we make it part of the sudoers group, so we can become root if need be. We set the working directory, and then we switch user. Yep, and then we'll need some place to put our sources, because the goal will be to compile an application, so we'll need to inject the sources inside our container, so I'm creating a directory for this. The executable we're building is the ELISA processor, aka processor X, so that's why the file is called like that. And then some entry points. So you saw when I was running the Debian image, by default it was running bash. Bash was the entry point of that image. And I want my entry point to be the script that will actually perform the build. So this entry.sh script will call CMake and then CMake build to build our product. And then a couple other things we can do is we can use this from keyword to use what's called image layering. And so all of this until now will be our production image. And then maybe for development, we need some additional tools, so we can add those at the end. And using overlay file systems again, Docker will build one image, which is all the stuff up to production. And then for my development image, which is just like more stuff on top of that, it's just another overlay file system with just the diff, which is nice because that means you can have a lot of different versions of images that use similar things like Debian as a base without like completely blowing up your disk usage, which is another advantage to Docker. If you're using VMs, every VM image is going to have your entire system on it, and it's going to take huge amounts of disk space. Then we need to build it. So for this, we use Docker build, and we give it the path to the Docker file, the target we want to go to. So in this case, we want the production image, and then we can tag it to give it a name. And then we can run it. So to run it, we'll need to inject the source code that we want to compile into this container. And for this, well, we'll use a feature called Docker volumes. So I'm creating two volumes, one for my build products. And because I'm using VCPKG and I don't want to be rebuilding my VCPKG packages every single time, I want them to persist between builds because that takes a while. I'm going to also create a package for my VCPKG, a volume, sorry, for my VCPKG packages. And I'm going to use Docker run to start that container with that image. So you can see the image name is on the last line there. And I'm going to use the volume argument to mount our current working directory where our source is into the container in that folder that we created before. And again, that's just a Linux mount. So this is like almost no overhead. This is really fast. Whereas file communication between a host and a VM needs to go through some kind of like networking and virtual block device is super slow. On containers, it's really fast, almost no overhead. Another volume to get the build products and the VCPKG cache that's mounted in the right place. So then once you run it, it will compile, it will call that entry point, do all your compilation, and then somehow you need to extract the build from the container back into your host system. You may not need to do this, you may just push it to some binary artifact server and then just grab it from there, or you might want to get it back into the host system. So in that case, that's what we're going to do. And because here we were running it with RM, once this container is done, it will be deleted. So all these virtual file systems that we saw, this overlay FS for the container, will be gone. But the volume we created for that build product, this processor X build volume, still exists. So somehow we need to get to it. And sadly, there's no easy way of doing this. So one way is to run a dummy container. So here I switched the entry point to just be like the true command, mounting the volume in there. So now that container is running, then we can use Docker CP to copy files from that container that's running into our host system. And then we can delete, so stop and delete that temporary container and delete that volume, which only served the purpose of extracting that build. Now we don't need it for the next build, because next time we will want to start from scratch again. So that's step one. Step two, we'll probably want to run this on some CI system. So in my case, I'm using Jenkins. And we don't want to install Jenkins manually on our build machine, right? We want to use Docker. So there is a Docker image published for Jenkins, so we're going to use it. And you'll probably want to add some stuff because maybe you're running Python as part of your build script, so you'll need to add that. So you'll do a custom image based on Jenkins. And then we will get in what is called the Docker in Docker problem, which you probably will get to as soon as you start using Docker for CI, which is we're running Jenkins as part of a Docker container, but we want Jenkins to be able to run a Docker container for our build image. So how do we do that? So somehow we need to have that container be able to run Docker, the Jenkins image. So we need to install Docker inside the Jenkins image. So we do that, blah, 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 blah. All the groups. I'll skip this to be a bit quicker. Blah, 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 blah. And then when we run our Jenkins image, we want to access the same Docker instance as the one running on the host. And thankfully, this is very easy to do. If you mount this Unix domain socket, so var run Docker socket from the host into the container, then our Jenkins container sees the same Docker daemon as the host system. So we're sharing it between the host system and the Jenkins image. So we're kind of creating a tunnel between our abstractions. So we're kind of like drilling through them voluntarily. So sadly, that won't be enough. All abstractions are leaky. And the problem is when we start that build image, we'll need to mount the source. But because we're using this way of doing Docker and Docker, the mount point is relative to the host system, but this is running in the Jenkins image. And the Jenkins image has no idea where its workspace sits in the host system. And so the law of leaky abstractions got us. And this is a workaround. This is how I've seen it done. I'm not super fan of this, but it works. So we can add the following environment variables when we're starting our Jenkins container to basically tell it, hey, your workspace, this is actually where it is in the container, and this is where it is in the host. And then we can use this in our CI script to be like, okay, are we running in a container or not? If we're not, we just do the normal thing. If we're running in a container, we can do a bit of path manipulation to figure out what the mount point is for our sources in the host file system. And this is not super fan of that because that breaks all the abstractions. But that's the way I found it done on the internet. Last thing, running audio applications using Docker. There's almost nothing to say. It just works. So in my case, I'm using the Jack server on my host system, which will talk to our sound card via the ALSA driver. Jack uses shared memory in dev SHM to communicate between the server and the clients. So if you mount that in the container, then your audio application can just talk to your Jack server that's running in the host just fine. It just works. And that would be impossible to do with VMs. And then you can fine-tune thread real-time priorities and CPU affinities as you would do because it's not a VM. Bang on time. References. This talk was influenced massively by this first YouTube video. Highly recommend it. And to go further, if you want to do any meaningful work with Docker, you'll need to look at Docker Compose, which is a much nicer way of writing these Docker commands, which usually can become very long and have many, many arguments. So this uses more like a config file approach to starting containers and building containers. Thank you.